Yes.
So yes, I'm going to be talking about one of these second generation instrument ideas, and some of the science behind driving that. Thomas mentioned this. Got to start planning ahead over the next decade. What are the next sort of windows and capabilities we want to open up? I'm going to be talking about an infrared imager. Our acronym may need a little work there, but good for now. Observing in the infrared, why is that interesting? It's nice because there's a lot of diagnostics that sort of go throughout the whole atmosphere from the photosphere, where there's some iron lines there. The 1.565 micron line is very sensitive to weak magnetic fields in the photosphere. The chromosphere has the helium-1 10-830 line, which is a very interesting line. The way it forms tells us a lot about the upper atmosphere, and it also captures this sort of interface with the corona. We see things like coronal rain, and I'll show you a movie of that in a minute here. So that's a great chromospheric diagnostic. You see an image there on the right, taken in the 10-830 line from Big Bear with the NIRIS instrument, which is a sort of an imager in the infrared for the 10-830 line that's been doing a lot of great work there. And you can see that sort of structure of this jet near the limb. And then there are a couple of coronal lines in the infrared that are great. The 10747 and 10798 lines are a great pair of iron 13 lines. They have good, they give us some density diagnostics. And I think Tom Shad will be talking about those tomorrow. So we can get this great chromospheric magnetometry. We can do coronal spectroscopy, look at wave propagation, flare dynamics. As Steve mentioned, waves in the corona are a great diagnostic, and they may also be important energetically. So it's important to look at those. We want to do this all at the sort of high spatial resolutions enabled by DKIST, from a half an arc second down to 0.05 arc seconds, at the diffraction limit for the 1 micron lines. That allows us to sort of resolve structures, get at the underlying physical processes, observe what's actually going on and make detailed model comparisons. And, I'll plug this talk by Benoit later about how important comparing observations and simulations is. So there's obviously, Thomas also mentioned, we have DL-NIRSP, we have cryo-NIRSP that observe in this spectral range. What are we interested in doing is actually doing this with imaging, where instead of using spectra or image slicers to take small pieces of a field of view and maybe map that up into a full field of view, but to actually capture a whole large, arc minute size field of view at once in the spectral diagnostics. That allows us to see spatially correlated dynamics. In the movie here on the right, you see the red box outlines the 10-830 image, and you can see this coronal rain coming down over there. Missed the credit here. This is a paper by Tom Shad a few years ago using an instrument at the Dunn Solar Telescope. The seeing's better in the infrared. We have more time to get these long sequences. We can do image reconstruction when we have these images taken at once, because we can sort of deconvolve the whole instantaneous PSF. And scattered light is lower, so we can do some of these coronal observations more easily. So I'll just jump into it. The idea is to use a dual Fabry-Perot system, sort of similar to the VTF and IBIS and other instruments that have made such good use of dual Fabry-Perots over the past couple decades to really get high throughput, reasonable spectral resolution, and be able to sample the whole field of view. The trade-off is getting fewer spectral samples typically than you would get with a spectrograph. And depending on your science goals, that may be the kind of trade-off you're willing to make. just some baseline sort of characteristics one could think of is sort of a spectral resolution of 100,000, where you could scan the helium-1 10830 line, a large range of that in just a few seconds to a minute or so, depending on the signal noise you want.
1 minute.
Okay. Oh boy. Why did it stop? Sorry. So the other trick with this will be, instead of a dual Fabry Pro, we can use a single Fabry Pro and do the coronal lines as well. Look at this 10747 and actually do imaging at resolutions, something like high C maybe. And so being able to do high resolution spectroscopy, resolve some of these coronal dynamics. We have a baseline optical design that uses all mirrors and is very small. It's only about 3 by 4 meters and fits on a horizontal plane. So, it's compact and can fit within the current, what space is left in the Coude room at DKIST. We've done some design work and prototyping of large Fabry Pros, 150 millimeters. And so we think we can place these in the desired configuration. And so, yeah, just in conclusion, this is a scientifically interesting instrument to do high resolution studies, look at these sort of large scale connections and sparse events like jets and flares and so on, and build.
Kevin, unfortunately, we have to finish up, so let's go.
Thanks. So the important one is, what science would you like to do with interesting in hearing people's interests?
And I want to remind everybody, we have time set aside for discussion after this, so we'll have plenty of time. So for those of you that want to ask questions or to have a discussion, either at the end of this when we do the discussion, or if we end up having time between, we probably won't, we can talk about it later. You can put it in the chat or raise your hand. So I think we need to move on.